All right, so let's talk arrays.
Get to actually use those now?
You're gonna, no, you're not allowed to. If I say you can't use arrays on the homework assignment, just don't even start it. It won't be worth. Yeah, actually, you can't solve it without arrays. Well, you could do it. It would be completely unfair. It wouldn't. It wouldn't even be a constructive assignment to do the homework in with just strings. But okay, so let's talk about arrays. Up to this point, shut up! All right, up to this point, we've talked about strings. So what's a string? A string is a collection of chars, right? But let's expound on that a little bit. So these are also read-only collections. We can put stuff into a string and we can get stuff out of the string, but we can't rewrite the string. We have to build a brand new string, right? So as an example, if we were to write something to remove vowels, so like tonight's homework, the homework that was due for today was to go through and print vowels, right? What if I said I wanted to write a function that removed vowels? So you might have, let's just dump this crap. Oh, did I push this? No. I'll just push that real quick, just so you have it. Let's see. Number conversion commit. When you look at Git, the current code is going to be this code. So you'll have to look at past versions of the file to see the different state of things. Okay. All right, so it's up there now. Yeah, so this has the number conversion stuff in it. But if you go in here and you click on history, you can see solution for homework 3 version of this guy. So we can just view that file. So there's the solution for homework 3. Make sense? Yeah. That's kind of like the nice thing about GitHub, is you can view multiple versions of the same file.
So we cannot upload the other files to the same repository if we want to?
You can if you want to. I'll look at timestamps, so I'll see when you last updated something. I usually, if it were me, I would start a new repository for each homework assignment, but whatever you want's fine. I'm pretty decent with tech, so I'll probably figure out what you're trying to accomplish one way or another. Okay, so for example, if we come in here and we got this stuff, it's just in our way. And let's say we write a function, static string remove vowels from string S. So ultimately what we want to do here is we want to return a brand new string that is the original string with the vowels removed from it. Okay? So we'll start off my little map string here. So A-E-I-O-U, A-E-I-O-U. And as we're going through and we're identifying vowels, we want to keep non-vowels, but we need to keep them somewhere. We can't pull them out of the existing string because the string is read-only. We have to build up a new string, keeping only the things that are not vowels. That make sense? So we're going to create a string answer. This guy will start off as the empty string. We'll go ahead and loop through I as we usually would. I is 0, I is less than s dot length, I plus plus. Each time through, we'll ask if map dot index of s dot char add I is equal to -1. So if the current dude we're looking at is not a vowel, that's what that says, right? If when I check the vowel string, and if it's not in there, if it returned to -1, that means it's not a vowel and I want to keep it. Why? Because my job here is to remove the vowels. So we'll say answer plus equals s.char add I. Then in the end, we'll just return answer. So now we can do like a system. HELLO, and we should be left with HLL. So there's our HLL. We removed the vowels, but that's what we said we did. But what we actually did is we went through this string. We didn't remove anything. We just held on to non-vowels inside of a brand new string. We built a new string. Make sense? So that's what I'm talking about here where I say that, well, not that screen, this screen. Strings are read-only. That's not a bad thing. You know, I think I mentioned when we first introduced strings last time that Java is a string-based language, and Java is not alone. C#, C++ to a lesser extent because that was during a time when standards weren't really around. There's like 4 different ways of representing strings in C++. The most recent version of them, something called C strings from the standard template library, is pretty good. Okay, but C++ is, there's several different standards there. But Java, C#, Objective-C, all of the web programming languages, PHP, Ruby, all those guys, JavaScript, strings are really, really malleable. You can do almost anything you want with them. Okay, so we don't want to look at this as a downside of strings. But we also want to go back and think about the thing about the right tool for the job. Strings are great for a lot of things, but they're not great for everything. All right, so let's look at we're going to look at things called arrays, which have the benefit of being collections of things that aren't necessarily chars, but then have the disadvantage of not having as much stuff built in. So we've already seen strings can do some interesting gymnastics themselves, right? They can tell us their length. They can give us a character at a certain place. They can give us the index of a character. They can convert themselves to uppercase. I bet you can guess they can convert themselves to lowercase. And they can do a whole bunch of other crap. All right, we're going to look at documentation probably next time when I introduce objects. But they can do a bunch of stuff. Arrays can't. At least not directly. They sort of can, but they have some help in the language. But we don't know about that anyways. But they do give us the flexibility of holding different kinds of values, and they also give us the flexibility of being read and write. All right, so let's talk about arrays at the high level. We've actually already discussed this when we talked about the history of our languages, right? You know, C had arrays. What's an array? It's a collection of like values stored within a single variable name. Okay? Now, the syntax. So, for example, we can have an array of numbers. So, you know, an array is going to look something like this. Let's go to this screen. I'm going to create a small array so I don't have to draw too much here. So we're going to say a 2, -4, -1, 8. Let's give us one more. And 1. All right, so that's going to be our array. And I'm going to so just like strings, arrays are indexed starting with bucket 0 all the way up to the length -1. Here are the values. Syntax for creating an array. Right in this particular case, we have an array of integers. Okay, so strings are an array of chars. Well, under the hood, strings are implemented in terms of an array of chars. We are now writing we're one level under the hood. We've ripped the hood of the car off, and now we're in there. We're working with a little bit something that's a little bit closer to the metal. That gives us some advantages and also some disadvantages. All right. So syntax for creating this guy would be just like any other variable. If we define a variable, it's type followed by var name equals value. Okay, that's the case for any variable. For us here to define this array, we would say integer array, if we call this guy AR, is equal to a new integer array of size 5. Okay? So that will give us a blank array with 5 buckets in it. So it'll be indexed 0 through 4 like this, but there will not be values in here. We would have to put values into this guy. It's an empty structure capable of holding values. So that one line of code there gives us this guy, an empty husk. Okay, we went to Walmart. We bought a shoe container, okay, a thing to hold, a shoe organizer to hold shoes, but we have not put shoes into it. We brought it home, we built it, and it's got empty cubby holes in there. All right, that's our starting point for an array. Now we want to talk about this new keyword here. Very, very, very important. It's going to be a big part of our lives moving forward. The new keyword. This is how Java asks the operating system for new memory. I like to think of this guy like our real estate agent. So if in real life we're looking to buy a house, well, let's say we're looking to build a house. That's really what we're doing here. We talk to a real estate agent and they go and find us a plot of land. The address of a plot of land big enough to build the house we want to build on, right? So if I say I want to build a 4,000 square foot house, and let's just assume yards don't exist, okay, and we give them the dimensions, she's going to go and find us the exact plot of land that will fit the house I want to build. Okay, and they come back and say, here's the address where you may build your house. Okay, they're not in charge of building the house. They're just saying, here's your memory. I've let the operating system know that you're going to be using this memory. They won't give it to anybody else. This is where you can go build your stuff. Make sense? That's what the new keyword does. So specifically in this case, the new keyword is asking the operating system for enough memory to hold this many of those guys. We talked about ints are 32 bits, right? So that's 160 bits of memory that we need to hold 5 of those. Okay? Arrays require something called contiguous memory. And this is going to be a huge theme in the next course, the 837 course, okay, which I encourage all of you to take. I mean, because as you're going to find out, as you're already finding out, the chances of you coming out of 8 weeks of programming as a proficient programmer is pretty slim. It just takes more time than that. So I would tack on that. Personally, I would tack on the second course. If after 8 weeks you decide programming's not your thing, then, but I don't know if 8 weeks is enough time to decide it's not your thing. But in any case, the entire second course surrounds this concept. So arrays, so I like to call the second course data structures. We actually do Android programming in that class, but we do it in the context of these things called data structures. And a data structure is a structure for holding data, just like I just mentioned a few minutes ago about the shoe bench, right? Or the shoe container. So you go to Target, you go to Walmart, you buy something very specific for holding shoes, right? It's perfect size cubby, well, except for my size feet. You know, I could put one shoe per cubby, all right? But generally speaking, it's built specifically to hold a shoe, all right? So that structure is built for something specific. Arrays are kind of our first data structure, right? And these guys are very powerful. and they're very fast. And one of the things we're going to talk about in that next course is the difference between arrays being fast and memory inefficient, and we'll talk about why they're memory inefficient here in a few minutes, compared to well, our starting point for that next course is something called a linked list, which is relatively slow but memory efficient. Okay? And the reason why arrays are considered to be memory inefficient is because they require contiguous memory. And what does that mean? This means memory next to each other. Okay, very important. So when we send that new keyword out, the real estate agent for us, when we say, hey, I need a plot of land big enough for my 4,000 square foot house, it's not acceptable for the real estate agent to come back and say, well, you can build 400 square feet at this address and 800 square feet over here and 1,300 square feet over here. That's not going to fly, right? And unless, I guess, maybe if the real estate prices are really cheap, maybe you can get into the business of those the tiny homes. See those? They would have to build me a bigger door. I mean, they're kind of cool. I mean, I like watching the show because it's really, innovative, some of the stuff they do. It would be good for my wife. I have a pocket wife. My wife's little. I don't even have to buy a plane ticket half the time. I put her in my carry-on luggage. Yeah, my wife's like 5'4", like, I don't know, 110 pounds or something. So she would fit in one of those fine, but I mean, I seem petite, but in real life, I'm pretty big. So but it's interesting. But in any case, that wouldn't fly in real life, right? We wouldn't send the real estate agent and expect for them to come back with 5 different addresses. Okay? We want to build a 4,000 square foot house. The implication is I need one plot of land big enough to hold 4,000 square feet. Okay? Same thing's true here with arrays. When I tell the real estate agent I have 5 integers, I want to build a structure big enough to hold 5 integers, the real estate agent's going to go out and find a plot of land all in a row right next to each other that can hold everything that we want to hold. Okay? So that's considered to be memory inefficient because we've now you could have a situation where you have, let's use a bigger array as an example. Let's say we have a 1,000 element array. All right? So let's just say, for the sake of argument, each element is large enough that what we really need is 500 megabytes of memory, just arbitrarily picking. So I need 500 megabytes of memory to store this. That's a big array. That's not something we're going to run into very often, but let's just say for our example. So we have 500 megabytes of memory we're going to need to store our stuff in our array. So now we're asking the real estate agent, the new keyword, to go out and find us 500 megabytes of unused memory next to each other. Okay, all in a row. Now, you could have a situation where you have a total of 500 megabytes of free memory in the system, but it might not be all right next to each other. So you may not actually have enough available memory in a row to fulfill the request. That makes sense? So because of that, arrays are considered to be memory inefficient. Don't confuse that with a statement that says arrays are bad. They're not. Memory inefficient does not necessarily mean they're bad. It's a trade-off. Because the opposite side of that is because arrays require memory to be contiguous, they're fast. And I'll explain why they're fast here in a minute. Okay? So here's the deal. When I say, operating system, go get me enough memory to hold this many of these dudes, that real estate agent's going to run out there, negotiate with the operating system, come back with a memory address. All right, have we talked about pointers at all in here? I think I mentioned something about removing syntax for pointers and adding syntaxes for pointers when we talked about the evolution of C to C++. Well, really the move from C++ to Java, right? We mentioned something along the lines that C++ let programmers make bad decisions because they can choose how they wanted memory to work. And Java took that decision-making away. And so a lie that is often told in textbooks, and one of the reasons why I don't use textbooks maybe part of it is I think I know better than the textbooks. Probably not a true statement, but I don't know. I seem like I have quite a bit of stuff in there somewhere. But I don't like when textbooks either sugarcoat certain concepts that shouldn't be sugarcoated or flat out mislead people. And I don't want to have to weed through a textbook to find that stuff. But a common misconception that Java textbooks specifically state is that something called a pointer does not exist in Java. So when we talk about pointers,
Oh, that's right. You did talk about that like the first day or two.
yeah. So pointers, this is a variable for holding a memory address. That's it. Okay. It's a variable for holding a memory address. Very, 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 very common in C and C++. All over the place. We had a special syntax for dealing with them. Kind of went away with Java, and realistically what's happened with the modern programmer is the idea of pointers. When you were a C++ programmer who moved to Java, you missed pointers. But if you've never been used to working with pointers and you went from Java to C# or something like that, you never missed something you didn't have, right? So think of pointers as kind of like with driving cars, kind of like a language with pointers is like a manual transmission, stick shift. And a language without pointers is like an automatic transmission where decisions are all being made for you. Most of the time, let's say, they're both going to operate similarly. An automatic transmission is going to make very similar automatic decisions to what a competent stick shift driver would make. Fair enough? With far less work on us. Okay? But every now and then, you're in a situation. So, for instance, I was in Colorado over fall break with my wife, and we went up to Pikes Peak, really high mountain thing there. And they tell you don't use your brakes, right? You don't want to use your brakes. To slow down, you want to do engine braking because it's better to put the burden on your engine than it is on your brake pads. Apparently, I was in a rental car, so I don't care. But it was fun for me to play with. I was in an automatic car, but I had the paddle shifter, so I felt like a race car driver, right? So you gear down to first gear, and you could only go so fast in first gear, so the gear slows you down. So in situations like that, a manual transmission would be beneficial, right? Or having some like the sport transmission, the car with the push buttons. So every now and then there is a benefit to those types of things. Now, where I don't like the lie is where they say pointers do not exist in Java. So let's throw that out real quick and just do this. Get rid of this remove vals. I'm going to go ahead and define our array real quick. Int array AR is equal to a new int array. We'll put 5 things in there. There's nothing in there right now, but we've requested the new keyword to go and get us a chunk of memory big enough to hold this many of these dudes. Okay? And it's going to return that to AR. So if we were to ask the question, what is AR? The first answer is AR is a variable, right? It's a variable. Okay, what kind of value is stored in AR? It would be easy for us to say, that's right. It would be easy for us to say it's an array. It's not. Prove it to you here real quick. System.out.println AR. Okay, I don't know about you, but that looks like a memory address to me. Those things that I say the textbooks say don't exist. That's a memory looking addressy thingy, right? That's what that guy is. So the difference here is that when the misleading statement that pointers don't exist in Java is made, the reality is this. Java does not have a specific syntax for pointers. The reality is that almost everything in Java is a pointer. Java makes the decision for us. And a majority of the time, it's less expensive to tell you the address of something than to give you the something. You know, the example we used was which is smarter to give. If you're inviting me to the party, do you hand me the house and tell me to open the door at 8, or do you give me the address of your house and tell me to be there at 8? A majority of the time in our real life scenarios, we are referencing places, giving people an address of where to go. I'll meet you at the library. The library has an assumed address that we all kind of have remembered that the address, the library here on campus has a location that we're familiar with, right? So a majority of the time, that's how real life works. Java's the same way. So when we say that pointers don't exist in Java, what we're actually saying is Java does not have a special syntax that allows the programmer to directly manipulate pointers, to directly manipulate memory. That doesn't mean memory isn't a thing. We just saw it. We wrote one line of code and found a pointer. They exist. We didn't have to like go through a whole bunch of rigmarole to uncover memory. It was right there. Okay? Yeah, here actually, if you want to write 0 lines of code, there's that memory address. You just write the one line to print out what was already passed in. Okay, this is a array of strings. That's what that guy is. Okay. All right, so going back here. So that's what our new keyword does. It gives us a plot of land capable of holding the stuff. So that new keyword ultimately creates something that looks like this. Let me make a little modification here, though. We're going to talk about that speed aspect of it. So just to keep the number simple, that's going to be 101, or 100 rather. Okay, so this is index 0, index 1, index 2, index 3, index 4, just like the char at 0, char at 1. So same indices through the array. Here's the values of the array. We've currently put nothing in there. It's an empty array capable. We could put shoes in when we're ready. We can put integers in here when we're ready. But under the hood, here are the memory locations associated with that array. We had no control over it. The new keyword did all that work for us. But one thing for us to notice right off the bat is notice these are right next to each other. They have jumps. You'll actually find it's a 4-byte jump. 32 bits, 32 divided by 8 is 4. It's a 4-byte jump. So here's one integer. 4 bytes later, here's another integer. 4 bytes later, here's another integer. So far and so on and so forth. And they're right next to each other in memory. That make sense? So I'm going to go ahead and I'm going to say, we're just going to write some more lines of code here. I'm going to say AR at bucket 2 is going to equal a 5. So I'm going to assign the value 5 to bucket 2 of my array. Right off the bat, we see that arrays are writable. So I can go to bucket 2 here and write in a 5. But what's actually happening? Human beings like saying this. We like saying, oh, well, I'm going to go to bucket 2 of the array and put in a value 5. That's not how computers work. Remember we talked about memory a little bit and said it's like one gigantic street in our computer with billions of houses on it? So you just have address after address after address. Computers are not going to say go to bucket 2. What they're going to say is when I say AR at bucket 2, this gets translated into this. It says start at memory location AR. Add to that 2 times the size of, in this case, an int. Base address of AR looks like it's 100. So let me go ahead and let's create a, here's AR, it's my variable. Get this guy a different color. And that variable has a value. Here's the value. And in this example, his value is going to be 100 because AR is said to point at the beginning of the array. Bucket 0 of our array lives at memory address 100. Here's a variable that holds a memory address. Yeah, they don't exist in Java. They do. It's a pointer. Right? So AR is a pointer. It holds a memory address which points to a place in memory where the actual array lives. All right? So when I say go to the base address of AR, we're saying go to AR, resolve it to its value. That's what we talked about that earlier tonight. Every variable resolves to the value it holds at runtime, right? So what is this guy actually saying? It's saying resolve AR to 100 plus 2 times the size of an integer. We've said ints are 32 bits or 4 bytes. So 2 times 4 is 8. So this actually equals 108. Where do we find bucket 2? Memory address 108. We can mathematically calculate where each element of our array is in memory because we're able to rely on the fact that it's stored contiguously in memory. Make sense? This is why arrays are fast. Now, again, computers are really fast. So most of the time, it doesn't matter whether we're using a fast array or a slow linked list, which we don't know about yet, and that's the next semester thing. But from a human being's perspective, we don't care. They're all the same speed. All right. Did I mention last week about the Grace Hopper nanosecond thing in here? So have we heard of Grace Hopper? She's let's say the first computer scientist. She's a lady. Well, you've seen all the signs up about our female computer science thing. Its name is Grace. It's named after her. All right, so famous. Fair to say she's kind of the founder of computer science. I think that's fair enough. And she was in the military. And she gives a really interesting talk. There's a YouTube video. If you're not friends with Grace on Facebook, do that or friend me, and I share a lot of the stuff. But they put a YouTube video up the other day of her giving a presentation to some people talking about time, specifically nanoseconds. As human beings, nanoseconds aren't how we organize the world, right? Like, how many of you would be able to tell the difference between 5 and 1,000 nanoseconds? Human beings don't perceive that at that level, right? Okay. How many of you could tell the difference between a nanosecond and a microsecond? None of us, right? That's not our world. Okay. We deal in seconds, minutes, hours, and days, right? And even if you asked me to tell the difference between 17 seconds and 19 seconds, I'd be roughing it, right? We're not going to be real precise even at that. But what she does is to bring it into kind of a reality. She talks about nanoseconds in terms of theoretical maximum speed of light. So right off the bat, we're like, okay, well, that doesn't sound like it's any easier. But what she does is she translates it into a piece of wire. 1 nanosecond is an 11.5-inch piece of wire. That's what it is. It's a physical piece of wire that's a little bit less than a foot long. So, she once had to, the video talks about her explaining to an admiral or something like that in the military, who was complaining something was taking too long to communicate with some satellite. She said, well, each nanosecond is 11 inches, 11.5 inches, and there's a lot of nanoseconds between here and space. And it's got to go there and back. So when we start thinking about things like that, we as human beings can start conceptualizing what a nanosecond kind of is, right? So at this talk, what she did is she handed out nanoseconds to each person in the audience. And then she said, well, let me show you a microsecond. I'm not going to give you all one of these because I only bring one. So she pulls out a backpack and she brings out like a big coil of wire. It's like, I think it was like 130 feet of wire or something like that. That's a microsecond. All right. So from us, nanoseconds and microseconds are indistinguishable for a human being in terms of our perception. but we can understand the difference between 130 feet and 11.5 inches. That makes sense? That's the relative difference between those values. Okay, so but kind of what got me on that is this idea that we need to live in reality, and this is something I think is especially true with IT professionals, because your whole business, IT professionals deal with people much more often than computer scientists do. Okay, because you're bridging that gap. I like to say that computer scientists they're opposite sides of the same coin. So computer scientists spend about 70% of their time creating new stuff, writing software. 30% of their time they're utilizing tools that already exist. IT professionals are doing the other side. 70% of the time an IT professional is going to be utilizing tools that already exist, and bending them to their will to solve some problem for consumers. 30% of the time they're going to be creating stuff, okay? But the IT professional spends a whole lot more time interacting with end users, okay, than computer science folks might, okay? And when you deal with making end users happy, it's all about their perception, okay? Not whether or not it actually is fast or whether or not it actually is slow, but do they believe it's fast? Did it feel fast enough for them? That kind of stuff, right? All right, so being able to relatively explain some of this stuff, I think becomes helpful, but also we have to have our own understanding because we're all people. Just because you know more about technology than they do doesn't mean that we're all completely lost when it comes to the time frames that computers operate in. All right, so punchline there is just because I'm saying arrays are fast and other things are slow, 99.9% of the time, we're not going to notice. We can use an array in the most inefficient way possible. And we'll talk about that here in a few minutes, but it's going to feel fast to us, even though we're just being destructive. Okay? And I guess what I'm saying about that is when we created this array, so let's just talk about it now. I specifically said my array has 5 buckets. I sent that new keyword, I sent my real estate agent out on a mission to find me the perfect size land for that 5 bucket array. What if I then decide I need to hold 6 things? The real life example is this. Let's say I build a house, got the perfect size land for the house. And then I decide, you know what? I want to add a deck. Put a nice hot tub out there in the deck, right? Well, so what do we got to do? Real life, what do? We add a deck. Not in the array world. The array world, we go and find another plot of land that's a little bit bigger than the current one. We rebuild the entire house, plus the deck. Then we burn down the old house. Didn't have a deck. And now we use the new house. Wait a minute, we need a swing set. See where we're going here? Would not be efficient in real life, correct? We wouldn't just keep burning down houses to add little new features to it. But that's horrifically inefficient on a computer. But we probably wouldn't notice as a human. You would have to be really, really abusing that idea in order to start feeling the delay that you're causing on the system. Because computers are so fast. All right, so that's why I really encourage you as you're going through this stuff, and hopefully you kind of got this beat into you over this last assignment. Don't look for ways to take shortcuts. Do things in such a way that it's clear to you what you're doing, even if you think there's likely a better way of doing it. Because the best way of doing it and the worst way of doing it is probably not going to be noticeable to you from a perception standard. Later on, after you've gotten some experience, after you've gotten some confidence, you'll start naturally making things more efficient. Okay? But even then, I personally think that chasing efficiency is only important a very small percentage of the time. Writing easy to read code, writing things that can be managed by the next person, even if it's not the most efficient mathematical solution, is far more beneficial than saving yourself a couple of CPU cycles at the cost of having something that nobody else can maintain. You know, and that's something you're going to run into as an IT professional. You know, you're constantly using other people's stuff. You know, you're using Microsoft product this, and when something is poorly documented, it's a nightmare to use. Doesn't matter how well it works. You know, so you're already in the IT industry. So at some point in time, you have had a product that once you became the guru of it, it was great. But the ramp up period, while you had to like learn how this thing worked with no documentation, or the documentation was in poorly written Egyptian.
Or, you know, you use the other example of bending it to your will. More often than not, you know, you end up using a product that sort of works for what you need, but then, you know, you put it in, it solves 10% of your problem. You spend 90% of your time bending it to make sure.
Yeah, sure.
And customizing it.
Right, but you certainly appreciate well-documented stuff. So if you have a product that somebody else wrote, I mean, they didn't know the problem you were trying to solve. When companies like Microsoft and, you know, the other enterprise companies, when they create a networking type product or an IT type product, they're trying to hit the sweet spot. You know, they're saying, we think most of our customers want to solve these problems. Okay, and the hope is that covers 85% of what you need.
They state 80%.
Yeah, yeah. And then what you have to do is then you have to bend it to get that other 10, or write your own little bit to get your other 10. That kind of stuff. Most of Microsoft stuff, it has scripting languages built into it, so you can modify it as you want. That's where this programming skill set comes in. All right, so yeah, I'm a big yeah. In general, I think I mentioned this several classes ago. Microsoft takes a lot of heat when Microsoft makes some pretty good stuff. They're just kind of a big target. Typically, places that run a Microsoft ecosystem end to end are every bit as happy as people who run an Apple. I mean, nobody runs a server setup for Apple. I mean, that's not. You would have to be in a very specific setup, but people who have everything Apple and everything just works are happy. People who have everything Microsoft, everything just works, they're happy too. It's the same thing. They're both proprietary setups, right? Their stuff works great together, and try to make it work with somebody else's stuff, and you'll have a better chance of getting Microsoft stuff working with other people's stuff than you will with Apple. So who knows? But in any case, this is why it's fast, is we can calculate where something lives in memory. Similarly, if we want to get the value from bucket 2, exact same thing, we would say we can do something like a system.out.println AR at bucket 2. That's us reading from bucket 2. Exact same math happens. We go and find the memory address, but we use the same syntax to get a value as we use to put a value. To put a value in bucket 2, we just put this syntax on the left-hand side of the assignment operator. It's catching the value that we're trying to put in there. Make sense? All right. So, having said that, let's do some stuff here. I'm going to create a function here called fillArray. So let's write a couple of methods. So we'll say static void fillArray, and this guy is going to take an integer array as a parameter. All right, and now let's just have it take in some values too. So int val. And what we'll do is we'll just fill the entire array up with whatever val is. If we want to put a bunch of 5s in there, we'll put a bunch of 5s in there, that kind of thing. So the first thing we need to do is we need to run through every element of our array. This is almost identical to how we do it for strings. Almost, one little change. For int I is equal to 0, I is less than ar dot length, no parentheses. I'll tell you why later. There's a good reason why. And it's going to happen next week when we talk about objects. There's a whole bunch of stuff I'm kind of hiding from you. For instance, you see me do a lot today, like when I call this function, we're going to say fill array like that. I would never write it that way. I would write it like this. Driver.fillArray. Let me show you why here in a second. Let me just finish this one. All right, so there's my function there. And the reason I always say driver.fillArray is this. I just start typing it, and I can just press enter. And it automatically fills it in for me. Okay, there's a good reason why driver before it makes sense. I'm not going to tell you right now, but there's a good reason. Next week it'll make sense because I'm going to be explaining the other side. I can't explain this side without being able to show you the alternative.
But that's only going to work if you have a function already defined later.
It's only going to work if you have static in front of it. Yeah, it has to do with the static keyword. So feel free to do this now if you want. I mostly do that kind of stuff so I don't make spelling errors. It's not required. Okay, so in any case, we'll say driver.fillArray. I'll pass it my array. Let's go ahead and fill this guy with 7s. And we'll run this, and nothing's going to happen. It did get filled with 7s. All right, so great. Let's go ahead and write another function here, static void. Let's call it print array. Int array AR. How many elements are in AR?
5.
Here, I'll give you a fighting chance. How many elements are in LOL?
No, because we haven't it's whatever.
How do we keep walking into the same wall? There's LOL.length number of elements. This is a function, right? Somebody's going to call this dude. Somebody's going to pass in an array. How big is the array? Let's ask them. All right. So to print this array, we'll do our same loop for int I is equal to 0. I is less than the number of elements. I plus plus. Yeah, that's one thing you'll notice is Eclipse is a little slow for code completion. Pretty often I type faster than it keeps up. So, and I make spelling errors, I guess, reasonably often. So you might start getting used to using the tool as it starts doing command completions and stuff like that for you. Okay, so we'll go through here. We're just going to say system.out.println. We'll print it out 1 per line. AR bucket I like that. So we'll fill our array. Then we'll say driver.printArray AR. And we'll see all of our 7s. Now, we should all be a little concerned right now. I built this array right here. I passed that array to my fill array. I didn't return anything from fill array. I didn't overwrite AR with the new version, the new filled version of itself. I then passed AR into print array, and I saw 7s. Why is that? All the other methods we've written today, when we were passing in strings and stuff like that, we had to receive the value that was returned. Then we could pass that value into something else and do something with that. Here it's kind of like magically happening. Weren't we inside? I mean, our model here isn't any different, is it? When I filled this guy up with 7s, and then I called print array, and I passed it AR. What's the value of AR? What do you think is going to print out there for the value of AR? I've already seen it today. Memory address, pointer. So there's a nice memory address. That's not a bunch of 7s. That's telling me where I can find all those 7s. When I passed it, when I said fill array, I passed it AR. I passed it a memory address. I told this dude, hey, go to this memory address and throw some 7s in there. When I called print array, I passed it a memory address. I said, hey, go to this memory address and spit the crap out you find there. Print it to the screen. Make sense? Both of those guys went to the same memory address. I'm passing in a value, but the value does not resolve to a literal value like a 5 or the string hello. It resolves to a place in memory. So I don't need to return these values. When I change something in memory, we used the example when we were originally talking about some of the stuff where I said if I gave you the address of my house and you went and spray painted my garage, when I get home, I'm going to be surprised. I'm going to see spray paint on my garage, right? Okay, because you made a modification to a single place in memory, a single place in society. And anybody else who stumbles upon that same place is going to recognize your changes. Does that make sense? All right, so this is considered something that has side effect. When we pass an array into a function, changes made to that array will have side effect. Did we talk about side effect? Okay, they will have side effect because we gave it the address. Okay, as opposed to when we give something the value, if I pass it an integer, kind of like handing somebody a quarter, changes to that quarter don't impact the other quarters in my pocket. You got a copy of it. Make sense? All right. So I'm going to go ahead and we're going to learn about some random numbers. I'm going to fill our array up with random numbers instead of just values. All right, so to fill an array up with random numbers, I'm going to need to use the random class. And we're not going to talk too much about the details of how this thing works here. I'm going to go ahead and import java.util.random. Put it up here for me. So this is what was required to use this other object. So the string class comes with, there's a hidden thing up here, import java.lang.star. That's there even though we don't see it. That's the core Java language. Inside there we have ints and strings and print system.out.println, all that crap lives in there. Well, the random object isn't part of java.lang. It lives inside of another package called java.util. It's some extra stuff. We'll talk more about that, but for right now, if we want random numbers, we import java.util.random. And as you saw there, Eclipse will do it for you. It'll underline the word random in red and say, do you want me to import this for you? You say yes, and it puts the line up there and everybody's happy. Okay? So now we have this, this random object. So what we're going to do is instead of filling with val, we're going to say r.nextInt. And I'm going to go ahead and just put 100 in here. There's a couple different versions of nextInt, but for right now, this is just how you define. This will generate a number between 0 and 99. That's what this will do. Okay? So now we can put some random data in there. So we'll go ahead and we'll fill our array. We should fill it up with random numbers. Then we'll print our array, and we should have a randomly filled array. I run it again, different numbers. Run it again, different numbers, so on and so forth. All right? So I have an array, and it just so happens that my array is not sorted. And I would like it to be sorted. That means I'd like the 5 to come first, then the 23, then the 44, then the 70, then the 72. Now, right off the bat, as a human being, we can look at those 5 values and we can put them in order, right? That doesn't seem like a difficult thing for us to do. If we had more than 5 values, you had 40 or 50 values, it'd be a harder job for us, right? But we need to slow ourselves down and ask, how did we put that in order? Right? Well, so we can certainly have an approach and kind of MacGyver a solution where maybe we go through and find the very smallest value, move that to the top. Then we find the next smallest value, move that to the top, so on and so forth.
What do you do, compare?
Hmm?
Just do a compare, random compare?
Well, we do, less than and greater than and that kind of stuff. So we're going to introduce 2 different sorting algorithms. We're going to look at bubble sort, and then we're going to talk about merge sort. So we're going to implement the easy one in class. And then the hard one is your homework assignment. All right, so.
Can we switch?
What fun would that be?
So it would be for us, everything is fine.
All right, so let's look at bubble sort. So bubble sort, we're going to call this easy to implement, not that efficient, but we probably won't notice. All right, so the premise of bubble sort is we go through each value in an array and we bubble it towards the top until we've moved it as far up as it can go. That's why it's called bubble sort. Okay, so let's look at this in passing. So let's just grab our, well, actually we can just do our numbers like this. So let's say that we have 14, 2, 9, 1, 7. Good enough. All right, so that's my array. 14, 2, 9. So what I'm going to do here is we're going to steal all of that stuff. We're going to forget about the memory addresses right now. At this point, we understand that they're there, but they're not something as a programmer, especially a Java programmer, that we're going to have to manipulate. But we understand how these guys mathematically work now, right? So when we look at bubble sort, here's our array. And we want to go ahead and sort this. So we're going to need several different values to do this. So we're going to create a variable. We're going to call this guy curStart. I'm going to draw a line, but curStart's actually just going to be an integer. So we're going to say curStart starts at 1. So this guy equals 1. That is the second value in the array. First value is at bucket 0, second value is at 1. curStart points to the position of the second value. All right? So the way this works is we ask the question, should a 2 come before a 14? If we're doing it in ascending order, 2 is less than 14, right? So it should. So since it should, what are we going to do? We're going to swap this 2 and this 14. Now in order to do that, we're going to need an extra variable. So we're going to need a swap variable. So we'll let the swap variable hold on to the 14 for a moment. Then we'll overwrite the 14 with the 2. If we didn't use the swap variable, we just lost our 14. Okay? So we'll store the swap variable first, overwrite it, and then we can copy swap back over to that guy. Okay? Now, we want to follow that 2 up the list, but we don't want to forget where our next starting place is. So we're going to need another variable. And I like to call this guy the follower. But when you say it, you got to say it in your head. It's got to sound creepy. It's the follower. You know what I'm saying? All right. So both of those started off at curStart. Because we just did a swap, because 2 should come before the 14, we did a swap, the follower follows. So now we asked, are we at the top of the array? We are. We have the 2 has bubbled up as far as it can go. So what do we do next? We adjust cur start by 1. We reset the follower. We ask the question, should a 9 come before the 14? Yes. We do the swap. The follower follows. Should a 9 come before a 2? Nope. So we're done. Increment cur start. Reset the follower. Should a 1 come before a 14? Yep. Swap. Follower follows. Should a 1 come before a 9? Yep. Swap. The follower follows. Should a 1 come before a 2? Yep. Swap. The follower follows. We're at the top of the array. Nothing else to compare. Increment cur start. Reset the follower. Should a 7 come before a 14? Yep. Swap. Follower follows. Should a 7 come before a 9? Yep. Swap. The follower follows. Should a 7 come before a 2? Nope. Increment cur start. We can go ahead and reset the follower as well. So let's think about the order and how this would happen. Then we'll notice we've run out of stuff. I think we'll magically find our array is in order. Make sense? See, if I'd given you that as an assignment, that would be too easy, wouldn't it? Makes sense like this, but now we have to write it, right? Okay, now we have to write it. So we needed 3 variables. Cur start, the follower, and that helper for swapping. So we'll go ahead and give ourselves static void bubble sort. We'll pass this guy the integer array. We'll give ourselves our values. Int swap. Int cur start is going to be equal to 1. And then int the follower. We'll also start off at 1. We're actually going to reset it each time, but all right. So how many times are we going to go through here? We're going to go through here as long as cur start is less than the length of AR, right? Because we do want to do it when it's the very last legal bucket. So while cur start, and you can do this with a for loop as well. We know how many times we're going to count, but we'll say while cur start is less than AR.length. Well, that's a true statement. What are we going to do? We'll set the follower equal to cur start. So that's resetting the follower, right? All right. Now, we're going to take the current value of the follower, compare it to the guy right before it, as long as there is a guy before it. If we should swap, we'll swap and follow. That make sense? So the follower starts off at cur start. Then we're going to say while, so we have a loop inside of a loop. So while we should bubble, while we should follow, when should we follow? We should follow when there is a guy before me, that is that the follower is not equal to 0. Okay, when we're not at the top. So we're not even going to try, if the follower is currently pointing here, we're not going to try to compare him to -1. So while the follower is not equal to 0 and the value at position the follower is less than the value at position the follower -1. While both of those things are true, swap and follow. Make sense? So while the follower is not equal to 0 and AR at bucket the follower is less than AR at bucket the follower -1. I know that this is a legal bucket because I wouldn't even be here if I failed this one. if the follower is not equal to 0, if the follower is equal to 0, this AND will fail. Guaranteed. Java knows that. Java will not even try to check the right-hand side. For an AND to be true, both sides need to be true. So as soon as Java runs into one false, it's not going to waste its time checking the other side. So if the follower is equal to 0, which means this is false, we don't have to worry about this one breaking, accessing bucket -1 of the array, because we won't even check it. Make sense? It's an important understanding. It's a computer programming concept to understand how an AND works, and that our modern programming languages, even historical programming languages, are aware of it. Okay, and they'll follow suit. So while I can check the guy before me, and I should swap, what will I do? I'll set swap equal to AR at position the follower. Then I'll say AR at position the follower -1. Actually, AR position the follower is equal to AR position the follower -1. And then AR at position the follower -1 is equal to swap. You could have also done it the other way, but so we'll store AR at bucket the follower, then we'll overwrite AR at bucket the follower, then we'll overwrite AR at the follower -1 with whatever we had stored. So that's our swap. Then the follower -. Follower follows. Right? Loop back up, check it again, go through the same thing. As soon as we fail this while loop, we failed either because the follower has reached the top or we bubbled as far up as we can go. We shouldn't do a swap. So when we fall out of there, what do? Cur start ++, loop back up, reset the follower. So there's our print array, driver.bubblesort AR, and then driver.print array. Here's our array. Did it just happen to be in order? No, it almost was in order. There's our original, and there's our sorted one. Yeah, let's run it again. We can get one. Yeah, this one's a little bit more all over the place. And let me do this. Put a nice little divider in there in our print. So here's our original array: 49, 2, 15, 24, 1, 1, 2, 15, 24, 49. That makes sense? Okay. So questions about bubble sort. All right. Now, let's talk about recursion. So recursion is when a function is implemented in terms of itself. That is to say, a function calls itself from within itself. All right, best way to look at recursion as an initial starting point is the factorial problem. All right, so we look at factorial. So like for instance, 4 factorial is equal to 4 times 3 times 2 times 1, which is 24, right? 5 factorial is 5 times 4 times 3 times 2 times 1. Isn't it also correct to say that 4 factorial is actually equal to 4 times 3 factorial? Isn't this 3 factorial right here? And isn't it correct to say that 3 factorial is actually equal to 3 times 2 factorial? 2 factorial is actually equal to 2 times 1 factorial. And 1 factorial is actually equal to 1. True statement, right? So factorial can be implemented recursively. So when we come in here, let's look at factorial. So we'll say static int factorial. This guy will take it an int n. We'll ask the question, if n is equal to 1, return 1. Otherwise, return n times factorial of n minus 1. So there's factorial. So if I say driver dot factorial of 4, and let's print that. This should give me my 24 down here at the bottom. If I say give me the factorial of 5, this should give me 120. That makes sense? So this is a recursive function, a function that takes, that's implemented in terms of itself. So this is tail recursion. This is what we do at the end. So at some point you need to stop. You don't want to have infinite recursion. Infinite recursion is bad. You get a stack. Here, so I'll just show you. I'll just take that out for the moment. Okay, this will break. All right, this will break. So we're going to force Java to flip out. And it's because of the way recursion is actually implemented. Whenever we call a function recursively, what we're doing is we're putting the current function call on hold. And we're calling that same function again. And the current function call has to wait for the next one to finish. So for instance, when we're doing 4 factorial, we can't answer this. We can't answer 4 times 3 factorial until 3 factorial finishes. We can't answer 3 factorial until 2 factorial finishes. We can't finish 2 factorial until 1 factorial finishes. And this is where it finally ends. Then we can bounce back up and finish this. Then we can finish this. Then we can finish this. Make sense? All right. So let's run this and break it. We'll see a Stack Overflow exception. So there's our Stack Overflow error. Because what's happened is every single time we call a function, we push the current one onto the stack, putting it on hold, and then call the function again. Push that on the stack, call the function again. Push that on the stack, call the function again. Eventually we run out of space on our stack. Stack of magazines gets too tall and Java says, okay, well, to protect the system, I put a limit on how tall the stack is allowed to get. So rather than letting you crash the computer, I just yelled at you. Make sense? All right, so we probably want to have our logic back in here. So now this guy is back to working. Make sense? Okay, so that is recursion. That's going to come in very handy for your homework assignment. Okay, so, well, any questions about recursion first, before we talk about what your homework's going to be on? Good? Recursion makes sense? Okay, I promise you, so here just like last time, truth in advertising, right? Recursion is hard. Just like right now you're trying to train your mind to slow down and break problems into little tiny baby steps, to train your mind to think recursively does not come naturally. Okay, so it's going to be difficult for you to think recursively. Kind of an interesting thing, our programming language theory class in the undergrad program in computer science, we use a functional programming language in there called Scheme. And Scheme does not support loops. So how do you iterate? You iterate over things using recursion. So these students are coming into there, and typically their skill in recursion is weak. Okay? They don't have enough reps in. So then they're thrown into the deep end, with the sharks in that class. And in the end, they're forced to use recursion for everything. And it's almost an overcorrection. They come out finding it difficult to not solve problems recursively. The reality is, again, it's the right tool for the job. If we were going to add some statements in here, we might say something like, recursive solutions are often very, let's say, tiny and, well, very tiny. So relatively few lines of code. Very memory inefficient. From a memory perspective, recursion is expensive. Every single time we call that function again, we have to remember all of those local variables we're currently keeping track of in this call to that function. Put that all on hold, and then call that function again with a brand new fresh set of the same values. Does that make sense? It's expensive. Now, that doesn't mean we shouldn't use it, because sometimes it gives us really elegant solutions. You can write something that, good examples can be your homework assignment. Your homework assignment at first glance is going to seem like a nightmare. The hint is, here's your hint for your homework, you're actually going to recursively call the function twice within itself. All right? We're going to talk about it right now. So I'll point out when you do that recursive call. All right, so we're going to do the algorithm just like we did with bubble sort, except I won't solve it. Well, I will solve it, but I'll solve it next week. After the tiers. All right, so we're looking at something here called merge sort. All right, so merge sort follows a thing called divide and conquer. It's a divide and conquer algorithm. The idea behind a divide and conquer algorithm sounds far more interesting than it actually is. It's that some jobs, just like in real life, can be solved by dividing up the work amongst multiple people, right? Okay, so if we're picking up trash in a park, do we have a conversation here at this point about like multi-core processors or anything? I talk about which is faster between a dual core and a quad core processor. Do we have that discussion in here? All right, well, so it's related to this. So which is faster? We'll ask it generically first. A dual core processor or a quad core processor? Which is better? So human response is quad core. More is better, right? All right, so let's say, and again, computer architecture plays into this and stuff, but let's say that your dual core processor is running at 3.2 gigahertz. So when I say dual core, I mean a processor that can theoretically do two things at once. Similarly, a quad core can theoretically do four things at once. Intel throws their hyper-threading in there and they talk about logical processors, but let's just keep this simple. Two things at once compared to four things at once. All right? And actually the best way to discuss this is a single core processor versus a quad core processor. So let's pretend like it's a single core versus a quad core. A single core can only do one thing at once. So let's say that I'm the single core processor. And I can change a light bulb at 3.2 gigahertz. All right? And the four of you are the quad core processor. And each of you can change a light bulb at 2.8 gigahertz. Who's going to win in our light bulb changing contest? Me! Changing a light bulb is not a four-person job. One-person job. I'm the fastest person. Probably because I'm tall and I don't have to get up the ladder. Saved myself some time right off the bat. Which actually is something we talked about earlier. My wife's little, so causes interesting things because I want things stored high. She wants things stored low where she can get to it. She's constantly stepping up on stools in the kitchen and stuff like that. When I could just touch the ceiling. All right, so, in any case, in that example, the single core processor will win because that one core is a little bit faster. All right. So, but now let's look at a division of labor problem. Let's say that again, I'm still the 3.2 gigahertz, and you guys are the 2.9 gigahertz, 2.8 gigahertz, whatever I said, and we're going to go clean up a park. All right. So I can pick up trash at 3.2 gigahertz. You guys can pick up trash at 2.8 gigahertz. Who's going to clean that park quicker, me or the four of you? You can each take 25% of that park. I have to handle the whole park myself. It's a division of labor problem, right? All right, so multi-core processors thrive in situations where we can divide things up, okay? Merge sort is a problem where we can divide up the sorting. When you write it, you're going to be at the mercy of whether Java assigns various recursive calls to one of the multiple cores. But the point is that merge sort is an example of a division of labor problem where we continue to divide the data up and sort parts of the list. We have a bunch of partially sorted things in the array, and then ultimately bring it back together. Make sense? All right, so that's the merge sort approach. So let's look at this as an example. So we're gonna steal this guy. And you will definitely find watching the video of this helpful when you go to do your homework. All right, I need to jumble this first. So we have a good enough, not sorted. Okay. So the very first thing so here's merge sort. Very first thing I ask is this sorted? Now, as a human being, we look at this and say, well, no, that's not in order. Okay. But the real question I'm asking is this entire array, by definition, trivially sorted? The answer is no. And the answer is no because it's not a one list. One lists are by definition sorted. If I have an array of one thing, it's sorted, right? So I'm going to ask the question right off the bat. Moons could align, this data could be sorted. Merge sort will not be aware of that. Merge sort is going to assume that since I'm currently looking at the entire array, it's not sorted. So what do? I take half of it and I call merge sort again. Recursive call 1. I take the other half and I call merge sort again. Recursive call 2. Now, first of all, I'm going to leave this guy up here for right now. I just called merge sort on this half of the data. I'm not even going to get to that second merge sort call until this guy's completely done, until I've dealt with the whole left-hand side of this array. That make sense? So I had to keep track of the beginning and end because this is the entire array here. This is bucket 0 to bucket 4. But when I divided it in half, now the portion of the array I'm looking at is bucket 0 to bucket 2. I haven't actually divided the array. I've passed the exact same array to merge sort. I've just let him know the part of this array I want you to focus on is begin is 0, end is 2. The original call was begin is 0, end is 4. So initially we call merge sort once. That's our original call to it. We say, I want you to look at the entire array. We look at the entire array. We say, well, it's not. End is not equal to begin, or begin is not equal to end. Therefore, it's not a one list. So what are we going to do? We're going to split it. We'll call merge sort on the left. Is this the one list? Is begin and end the same value? No. So we're going to split it. So as long as you always split it the same way, it doesn't matter which side is the heavy half. So I picked the heavy half. The left side was the bigger half before. I'm going to keep doing the same math to split it. So I'm going to call merge sort again, passing it 0 is the beginning, 1 is the end. Same merge sort call. I haven't changed the array at all. I've just told him to focus on a different part of it. Okay, so the hint here would be merge sort's going to take in 3 parameters. The array, the beginning of the array that you want it to focus on and the end of the array that you want it to focus on, because you're going to be looking at portions of the array. So here's that next call to merge sort. Is this the one list? No. Sort again. Is this the one list? Yes. Call merge sort on the right hand side. Is this the one list? Yes. So now you bring these guys back together, and now what you do is you do the merge step. So the merge step is going to require creating a second array. And what you're going to have is you're going to have two different pointers. Let's call this begin 1, begin 2. Begin 1 will point at the beginning of the first half of the list. Begin 2 will point at the beginning of the second half of the list. And we're going to ask the question, which should come first? The value at begin 1 or the value at begin 2? Value at begin 2. So we'll store the 1 here, and then we'll increment begin 2. Which should come first? The value at begin 1 or any legal position? Begin 1. So we'll get the 8. So now both of these guys are off the end of their individual lists, right? Okay, so begin 1 is out of bounds, begin 2 is out of bounds, so we have now sorted it. But we sorted it in this temporary array. So now we're going to copy the results back. So this is a 1, this is an 8. And now we're done with that merge step. So now we've bounced back up. That's the end of the left-hand call from there. Then we make the right-hand call. We notice this guy's a 1 list. We bounce right back up. Here's begin 2. Here's begin 1. I'll give myself one more little column here. So notice we create a temporary array that's big enough to house all the values for the portion of the array we're currently looking at. So we ask, which should come first? The value at begin 1 or the value at begin 2? A 1 or a 7? A 1. A 7 or an 8? 7. 7 comes before 8. Which should come first? An 8 or an illegal position? 8. So there's that. We'll copy our answers back up here. There's the 1. There's the 7. There's the 8. These guys come back together. We now have finished our original left-hand call. Now we're finally able to make our original second call to merge sort. Is this the 1 list? No. Split it. 1 list, yes. Call on the right-hand side. 1 list, yes. Now we're going to do our merge. So here's begin 2. Here's begin 1. Get rid of this guy for right now. Which should come first? A 14 or a 9? 9. Increment begin 2. Which should come first? A 14 or an illegal position? 14. By the way, what we're doing right here is called the merge step. So that's the 14. Now we know we're done. We'll copy the values back over. So here's the 9. Here's the 14. This bounces back up here. Now something we want to notice here is we have two halves of our list. This list is sorted in and of itself. This list is sorted in and of itself. So we have two partially sorted lists. Set begin 1 to beginning of the first list. Set begin 2 to the beginning of the second list. We'll do our final merge step. I'm going to need some more buckets here. Which should come first, a 1 or a 9? A 1. Which should come first, a 7 or a 9? 7. Which should come first, a 8 or a 9? Which should come first, an illegal position or a 9? Because this guy's off the end of his list, right? 9 should come first. Which should come first, an illegal position or a 14? Copy the results back, 1, 7, 8, 9, 14. They happen to already be in order. And merge sort is done. We just came back from our second call, our second original call to merge sort, and there's our ordered array. Make sense? So the hint is 2 calls to merge sort. Merge sort on the left-hand side, merge sort on the right-hand side. The code to solve this problem is relatively short. But the thought process is going to be complex because of the recursive thinking.
It anyways look complex, like the other one was bubble sort was pretty easy to sort. Then this one, so why we have this complex procedure.
For what we talked about a few minutes ago about multi-processor machines. If you have a million things you need to sort and you have 4 processors, now each one of those processors can handle 250,000 things. You've split it across because it's a divide and conquer type thing. Make sense?
That's the difference between 10 milliseconds and 100 milliseconds.
Yeah. All right. Questions, comments, concerns, bribes? No bribes this week? Maybe next week. This assignment wasn't hard enough?
I was watching one video of you having a record of eating that, I think, color or something.
Oh, yeah. I didn't tell that story in here.